Okay. So from my side, unmuted. Good. Let's give it a try. I don't want to yell at you, so I'm starting cautiously. I don't know whether the microphone is on.
No, there is no amplification, so it's only for recording.
Ah, it's just for recording?
Yeah.
Okay, good. So I'll start here with. So, thank you for having me here. I'm Peter Baumann, and what I'm going to present you is actually joint work of several people in my group. One of them in particular, Dimitar Mishev, whose PhD thesis is engaged in that work as well. But I would have to take a long list actually, to be honest, to give proper credit to everybody who has contributed to that. And not the least, of course, also the standardization bodies, where we had lots of discussion. It gave me a lot of opportunity to learn things, as I'm just a plain computer scientist that has stumbled into GeoWorld. And that's it, what I want to talk about multidimensional data that appear as spatial temporal data cubes. So, we have this funny term of coverage. This is age-old. Actually, only few remember that it originally was invented by Esri for a particular data structure. But meantime, it's decoupled from that. And they themselves were surprised to discover what coverages have become in the meantime. Coverage is catch-all terms that actually relates to feature. You know, in OGC standardization world, a feature is a geographic object in the end, something that has some location, space and time attached. Then we have a special kind of feature that is a coverage. A coverage is defined as something that may sound really strange, a space-time varying phenomenon. That wants to express something specific. If you look at, say, a highway here, and you take the A1, if you model that as a vector, then obviously the attribute A1 will be invariant. Over the full size, over the full length of this highway, it will be A1. So it's sort of static attributes that are attached. Here, however, if you take some image and walk from one location to another, the value changes. And that is what this expression wants to say. It changes as you go from one element to another. It's pretty clear that this kind of thing requires more storage space, and therefore the big data that we encounter, at least big in terms of volume, typically are coverages, not so much vectors. And actually it's not raster data only, if you think about that one, but you could generalize that as regular and irregular grids, as point clouds and meshes. We can sort of make this a little bit more graphic, more spicy. So we have a feature, and we have some abstract coverage, which actually has several subtypes, if you will, which also reflects history. We have the grid coverages, the first naive attempt around about 2004. That is not very much used today, and in particular not with geocoordinates, because it has some difficulties. I avoid the word flaw here. We had to improve on that, got rectified coverage, which is an ortho image, so rectilinear grids. And then the rest of it all was termed referenceable grid. You see, I cannot even pronounce it. Referenceable grid coverage. Nobody could explain me why the term was chosen. It's a little bit difficult, but it means irregular grids in the end, so everything else. That is historical development, like rings in a tree. Actually, we supersede this currently with the coverage implementation schema 1.1, where we introduce a general grid coverage, which brings all these historical developments together into something that is easier to handle, easier to understand, and in particular, one single concept. And that is what typically is known as data cubes. That is some arrays, some raster sets that have 2 dimensions, 3 dimensions, 4 dimensions, 5, whatever. And as you can see, they can have straight lines like ortho images. It can be curvilinear, like meshes following a coastline, or the strange things that people do in climate modeling. All of that falls into that category. But it doesn't stop there, because in the end it's point in space that just happen to have a particular constraint, that they all have neighbors. If you don't have that, If you give up that, then you come to multi-point coverages, that is point clouds. If you add curves, so bundles of trajectories, could be a multi-curve coverage, and so on, multi-surface coverage, multi-solid coverage. This is actually where we close the gap to city modeling, for example, city GML, also to CAD, computer-aided design. So we do not reinvent wheels, we just want to close gaps. This is an abstract concept, and that has been defined in OGC Abstract Topic 6, which is identical to ISO 19123. Abstract in the sense it does not prescribe a particular implementation, which means you can have divergent implementations, and you find that out there. So if somebody says, I'm interoperable because I'm implementing 19123, wrong. You find diverging implementations out there, and you have a very simple criterion. They all come with their own client, because crisscross coupling does not work. Therefore, OGC has added a concrete coverage implementation schema, which is a concretization that makes a few assumptions so that it becomes interoperable. And actually, we can do conformance testing down to the level of single pixels, saying whether an implementation is correct or not. In this sense, it's concrete. And then you can use client A to access server B. That is possible indeed, and that has been done. So that is the general thing. Stepping back a little bit, we can bring that into a very simple schema actually using UML. So it's a specialization of feature that has a domain set telling us where do our values sit. The range set, which are the values. You see, domain range, it's like a function mapping locations to values. And what we have added then over GML, for example, is the data type. What is the data type of our values? Is it temperature? Is it radians or whatever else? And this actually we took from SWE Common. So actually now we have a connection to sensor world. So sensor observations can be transformed into coverages without loss of semantics here. That was important to us. Still, there are quite a few data that people want to attach, different ones depending on their domain. And so there is an optional metadata package where I can put anything else you want. The coverage doesn't understand it, but it does transport it for you. So this is a way to carry along all sort of specific metadata that you want to remember. If you want to see that in GML, okay, here is an example for it, where you see the domain set with a grid definition. This happens to be 4-dimensional, lat, long, height, and date. So you have a regular axis for lat long. You have an irregular axis for height, with 2 levels in this case. And you have an irregular axis for time, also 2 levels. I didn't want to write more, I was lazy. This is mapped to a grid axis, and then you know where the points sit, and the point values you have here in the range set. And down there in the range type, you see what that means. For example, it's panchromatic. We have radians, reference to it, and we have the units of measure, and that kind of things. That is the historical way, because GML just was trendy at that time when it originated. But with CIS 1.1, if you favor curly braces, then here is the same thing in JSON. Domain set, range type. And the good thing is that it has the same semantics. We can map it. So you can do a one-to-one mapping. You are not bound to a particular world of standardization. And if you are into ontologies and into reasoning, then you may want to enjoy the RDF representation. Please look at it closely. I will rehearse it afterwards. So we have different formats available. If we step back a little bit, that means we can encode our coverage into a single file where we have domain set, range type, and the metadata. And we are informationally complete in the sense that it contains all of the definition if you use some format like GML, JSON, or RDF. Fine so far, but inefficient, obviously. You don't want to transport 10 terabyte encoded in ASCII, not really. So we need binary formats, okay? That is defined as well with a coverage standard. You can use any of those formats, and this is a growing list. We have more and more mappings defined. Obviously, this is incomplete sometimes. GeoTIFF is not able to handle all of the range type information, for example. But okay, you want it, you get it. Sometimes there are reasons for that. Maybe you just want to display in a browser, so you pick a PNG, knowing that you will not get the full information. So that is not an inconsistency. That is meant this way. However, sometimes we want to have both. I want to be informationally complete and I want to encode efficiently. Therefore, we have a multi-part encoding where we have a container concept, that we have some header, which is some informationally complete format, GML or JSON or RDF, and then you have links from particular elements into other files, and these contain then, say, the pixel payload, so they can be stored efficiently. Okay, so we can use historically, it was multi-part MIME in CIS 1.0, but in future that can be zip, GML, JP2, the safe format, Q package, whatever we want. And this concept actually allows us also to introduce collections of coverages to be transported, and it allows also to introduce tiling, multidimensional tiling, partitioning of objects. Some formats support that already, like GeoTIFF, for example. Others don't. Now we have a way to model that, to represent that, regardless of the format. So this is the coverages, the data structure. This data structure actually can be served by many different services. We tentatively decoupled that from the web coverage service. So a WFS, a web feature service, can serve a coverage as well, because the coverage is a feature in the end. Just depends on the implementation. So actually the coverages can float between different services, or in other words, can be passed on from one to the next. For example, from a sensor observation service into a web coverage service, and so on. Okay, I will focus on the web coverage service because that offers the dedicated functionality specifically for the coverages. This WCS standard is organized into set into a suite of standards, not to make life more complicated, but actually to make it easier. Because the WCS core is very, very simple. It's about the level of master thesis for a good student to implement that as part of a semester work. And then you get something that delivers a coverage or a subset of it. Subsetting means I can trim. That is, I do a cutout, but I retain the amount of dimensions. So a 2D cutout from a 2D coverage. Or it can be slicing, which reduces the number of dimensions. So from a 3-dimensional image time series stack, for example, I take out a time slice, which then is 2D. Or I do a time series analysis, then I get out a 1-dimensional coverage. So I can walk myself through the dimensions and can extract whatever I want to transport the minimum amount to the client. This you get back in the stored format if you don't say anything, but you also can request a format conversion, say into GeoTIFF, or you want a GML representation. And the service can decide which format it want to support. This is the mandatory stuff. Then there are different facets in the extensions, functionality facets, which a service may or may not implement. That makes it simpler for implementers because you don't have to code a lot until you have something ready, but you can say, I offer core and I'm working on extensions. It's good for those who want to buy an implementation or select an open source implementation because they can set up a list saying, I need WCS core and I need the range subsetting extension, I need the CRS transformation extension, and then everybody knows exactly what is necessary. And so you can negotiate and you have a clear understanding of the functionality that is to be delivered. Finally, we have application profiles, which is just some bespoke packaging of functionality for different purposes. Currently, we have satellite imagery, and metocean data is in the make. So that is something that I'm using we, because we actually have done that. I'm the editor of those things here. And so naturally, we use our Rasterman system for something that is used for implementing. And so we also have the implementation available, but many others do as well. So actually we get a common information space where coverage services interoperate. Okay, 5 minutes left. The funny word has fallen. Rasterman, Raster Data Manager. So that is our vehicle that we are building, a so-called array database system that enhances standard SQL with queries on multidimensional arrays. And behind that, tile streaming architecture, which is peer-to-peer, so fully parallelized without single point of failure. We are on OSGeo Live. OSGeo incubation was not where both parties felt happy with, so that we have abandoned. And what did I want to say? Yes, a couple of awards. Just to give you an overview of the architecture, we do a partitioning, of course, which can be any sort of partitioning to do optimization, like saying this particular region must be really fast, and for the rest, just do something meaningful, dear system. We have a parallel architecture where we have split queries over more than 1,000 cloud nodes. And this is our latest thing. This year we are going to be on board a satellite. Big fun for everybody in the team. And I hasten to say, these interfaces are not for end users. We can discuss a lot about GET versus REST versus POST or so, but actually I don't care. This is all just internal interfaces. People want to use their comfort zone, their tools. And so actually it's important that we just have this as a client-server tool interface, and instead we allow to plug in all the different things like Python, presented that yesterday, that allow people to work on data analysis, on just browsing maps, doing web GIS or whatever. And the standards are our friend, so we can attach client A to server B. Okay, now I've talked too much, so this one I have to shorten drastically. I guess I will just do this one. How many minutes do I have? 3. Okay. So just this one. It's embedded into the Earth Server initiative, which finances us via the European Commission, and we are very grateful on that, where we build up databases on 3-dimensional image time series and 4-dimensional weather data cubes. So we have the Sentinel data of ESA. We have ocean color analysis at Plymouth Marine Laboratory, National Computational Infrastructure Australia, European Centre for Medium Range Weather Forecast gives us 4-dimensional data cubes. And then we do a combination of data cubes between Australia and London, Reading to be exact, and combine them, visualize them in NASA Web Whirlwind. So in the end, what we are aiming at is a global federation where you can do anything on the data cubes that are stored here and there. If you want, offline, I can show you the demo. We don't have time for that now, but I can show you that data fusion already in a first version, let us say. Okay. I had wanted to talk more about OSGeo as well, because this I thought might be a good forum for discussion, but we don't have time for that. So I will skip all that and just stop here, I guess. 1 minute. Should I talk even faster? We can pitch up by frequency. I guess it doesn't make so much sense, but just to stimulate discussion, I cannot resist totally. So what I show you is just the summary thingy here of those things I wanted to discuss. I mentioned our incubation in OSGeo, and actually we were good friends except for one thing, the maintenance of the code, where they say all software should be free, and I say, why? We have that doesn't want to come. Okay, come on, come on, come on. Hey, don't try to outsmart me. Got it. Okay. Yes, I admit we have a mixed license model, dual license model. Is that bad? I mean, we have a full spectrum. We have the full commercial stuff, S3, as a placeholder. And then, on the other hand, this is what OSGeo wants. What about these ones? they should be accommodated as well. How much more powerful would OSGeo be if it would be inclusive and get all that in? Dirk Vriene is one of the proponents of such thinking, but it doesn't somehow get through. And in the end, the ESRIs don't care about our war between here and there. But the small companies, they suffer. Is that really what we want? Question mark. And with that one, I guess I really need to stop. Thank you, Anne. And thank you for bearing with me. So, yes, suddenly I have 5 minutes again. That is, you have 5 minutes. So please, flames on or comments or whatever. Okay, good. So thanks again and bye. Now, how do I get out without this thingy hanging up? That should work. It doesn't like to unplug when Windows is in full screen mode, so I need to be careful, but it worked now. Okay, thank you.
I definitely want to discuss with you about licensing and stuff like that.
Yes, why don't you do it? I'm here now.
We just turn off the microphone.
Go out on the back.
The rest of the records. Okay.
No.